Hello everyone, and welcome to Mox's webinar, A New Paradigm for Communication in Power Substations, IEC 61850. I'm Martin McHugh, and I'll be your moderator today. Okay, let's get started. We will have a 30 to 40 minute presentation with 10 to 15 minutes of Q&A. Today's presenter is Jim Tepper. Jim has 18 years of data communications experience, 11 of which are focused in the industrial automation space. During this time, he has written numerous articles for Automation World and Control Engineering magazine, and has recently written a white paper on cybersecurity for critical control systems. Jim's most recent role is focused on business development in the power market, but he also has been product manager of power-oriented communications equipment at Moxa for 8 years. Jim has worked for such companies as US Robotics, 3Com, Digi International, and is currently the Business Development Manager for Power and Utilities here at Moxa. And with that, I'll hand it over to Jim.
Wow, what an introduction. Thank you, Marty. It sounds like I'm some sort of god or something in this arena, but really I'm just a guy that knows a little bit about communications and a little bit about Substation, and I'd like to impart some of this wisdom upon you. Certainly I can't talk to all aspects of a distribution substation, but I can talk about the Ethernet aspect of it and even some of the computing portions of it. So I'm coming at it from a computing and communication perspective, and hopefully that'll give you a little bit of insight as to how you might be able to, I don't know, jump on board with the new trend of 61850. I start with this quote because I think it's interesting. The company Capgemini is traditionally focused in the, we'll call it commercial space. So what you'll find is that, Capgemini will do lots of research and study and consulting for corporate business oriented companies, offices, stuff like that. And they haven't really been too concerned with the down and dirty utility aspects until most recently. So the statement here is somewhat obvious. If investments in this area are made properly, effective distribution optimization will enable proactive grid management and assure reliability and efficiency of service. So yeah, we can become more efficient if we start using newer technologies and investments are made along those lines. But the most interesting part of this quotation itself is that a company outside of an industrial kind of application, outside of utilities, is making this astute observation. And that just shows you how mainstream these technologies are and how mainstream communication will become for the utility space and substations specifically. You may have seen things like industrial Internet of Things and smart grid and all of those neat buzzwords recently that all have to do with this. So let's move on. Our focus today is going to be on substation. So and as I'm defining substation here, it really spans the gamut. On the furthest left is really generation / distribution or substation, all the way to the right where you have kind of the end user connectivity, where it gets the transformers outside of the home. Mostly the information today will be focused in the center of this diagram from 330 kV down to about 10 kV and communications therein. But a lot of this can be applied to any area whatsoever because communications is a critical piece of infrastructure nowadays, and we'll talk about that. So generation certainly isn't a focus for 61850, but it is a place where it can apply. So even though we'll talk a little bit about distribution today, generation is certainly a point in which the power originates, and it still needs to communicate with that substation, so it's a good idea to consider some of those technologies. From a transmission perspective, it's the same thing. Once it gets generated, it needs to be sent. And if we're still communicating with those common protocols that we'll talk about within this presentation, we'll have some advantages that we can gain. Even all the way down to the AMR or AMI, it's automatic meter reading, automatic meter infrastructure. It is, these things can also speak some common protocols that can be recognized all the way back to the substation, therefore helping with potentially demand generation and allocation of power across the entire grid. Well, we're not going to focus on AMR, AMI today, although Moxa does have a few interesting solutions in that arena. We're going to talk about substation. Let's take a look at the current state of the power industry. This was a survey that was done earlier this year, so it's pretty fresh information, called the Utility Dive survey. And they surveyed a bunch of different utilities across the United States. And what they found was, United States and Canada actually, and what they found was that the most concerning piece that everyone has right now is really their concern with the old infrastructure. And that includes the physical pieces like the transformers and whatnot, but also communication, the ability to monitor those things. And then you kind of look down the list here, you see distributed generation. That's, something that's a big pressing issue, and things like smart grid and grid reliability, and then even cybersecurity. All of those things have to do specifically with communications, and communications can address those issues. It's good to see that people are kind of looking for some solutions out there. Then there's some other questions that were asked about demand response, the ability to shift power within different areas in your serviceable area. Everybody wants to do it, really. We're expecting a pretty big growth in this particular aspect over the next 10 years. But right now, 81%, they're planning at least to grow their demand response. One way, or the most common way to do that, is to make sure you are fully connected and aware of everything that's going on in your grid. And you need communications to do that, and computing, of course. So as utility planning to grow its efficiency programs over the next 5 years or so. And yes, of course, I think everyone wants to grow their energy efficiency programs, and that can be something as simple as turning off your AC during peak periods when there just isn't enough power to go around and they don't want to pay the extra high rates for generation. But you can certainly do that with connected infrastructure. You can cycle people's AC. You can use the Nest thermostat to program to turn down, turn down the AC, or I guess turn it up, as it were, to a higher temperature so that it uses less electricity. That can all be done and monitored through communications, of course. And then that's kind of an edge-to-core kind of concept there. But then, we see things like coal generation being retired in 2020. A vast majority of coal generation will be retired around that year. And then people are making the shift to other means of generation. There's been a pretty big shift to solar recently. The last couple of years, it's really boomed in terms of adoption percentage. But things like natural gas is the next trend. As we build these new generation facilities, we're finding that more people are using more communication technology to connect them, the newer stuff. So then it's kind of a trickle-down effect where the substations then need to fall in line so that everyone can communicate correctly together and become as efficient as possible. And then even the smart meters, as we talked about, the AMR, AMI stuff, it's pretty interesting from this survey. We're seeing that 92% of all utilities are using smart meters in their territory. That's a pretty high number. Now, they may not be fully deployed, but this number is increasing every single day. And that just shows that there's a lot of data out there that's fully connected. Why don't we make better use of it? So you think, another quote here from Navigant Research, the states like New York, Massachusetts, California, Hawaii, and Maryland are the forefront grid modernization. Really, they're early adopters and are transforming the utility business model to incentivize more active customer participation in demand response programs. So, you look at some of these states, and certainly they're not the only ones that are investing heavily in grid modernization, but they're realizing that if they do it, they can actually see a change in their, their capabilities and their efficiencies, and that reduces costs of running the utilities. So that's kind of a big deal. They're seeing ROI right away, even though they're early adopters. So today, the means of which that we're seeing these communications occur are through maybe some of these protocols here. Modbus ASCII, Modbus RT, Modbus TCP, even Modbus Plus. It's really scary. You see a lot of DNP3, of course, out there, both serial and Ethernet versions. The 608.70-5, Ethernet IP, some ASCII, and then there's a big category with other, because there's lots of other protocols. But what I'm talking about is pretty much a common protocol that most people are using, and these tend to be the standards. This new initiative, IEC 61850, what is this thing anyway? It's been talked about for years. Most people really didn't want to embrace it in North America for quite a while, and we'll talk about that in a minute. I categorize it as three different things in general, at least. One of them is our point of view, a manufacturer's point of view. It's an environmental certification. Can you survive in the temperature and the vibration and the EMI that's produced in these environments? So, you know, that's one aspect. Another aspect are, well, 61850, is it using a special protocol? Is it like Modbus? Is it different? You know, what is it? What protocols are they using? And then the concept or mindset as well is kind of like how you approach 61850. It's actually kind of like, I guess you could almost say it's a lifestyle. But it is a way of doing things. It's almost like a rule book that kind of says, hey, if you're connecting these things, you should follow this process. If you're connecting those things, you follow this process. Use this protocol, et cetera, et cetera. So next time someone brings up 61850, you might have to actually ask them, would you be a little more clear? Which part of it are you talking about? Are you talking about best use, best practices? Are you talking about the protocols? Are you talking about certs? What is it? Let's go into a little bit about the actual trends globally for 61850. It's very interesting because most people didn't realize the very first early adopters for 61850 was China. And it makes sense when you think about it because their infrastructure growth was off the charts back in 2010, 2011. So they started adopting the newest technology as they grew 2 substation deployments every single day. That is massive amount of electricity that they were putting into the country. So it kind of gives you, wow, that's shocking how much distribution put out there. So it's no wonder that they're trying to be as efficient as possible and use the latest technology to you know, make sure it's reliable and last a long time. So Wave 2 was an Asia Pac Rim type thing. The neighbors of China and whatnot have, of course, started adopting these technologies as well as their infrastructure grew. And then interestingly enough, Europe has just started coming on board with the adoption of 61850 and using that technologies. And here we are in the U.S. Kind of on the back end of it. Now, one of the reasons we are is because our grid's pretty good today. It may not be as efficient as possible, but it's pretty stable and generally has enough capacity. But what we're finding is that we'd like to find out ways to reduce our costs and increase efficiency over time. So we're checking into these new opportunities and saying, oh, okay, well, 61850 might actually save me a bit of money and time, so we should check into it. And luckily also we get to learn from the mistakes that were made in the first couple waves of deployment of 61850, and we can say, oh, you know, we should avoid that pitfall, we should focus on this and make sure it's all taken care of. So in a way we're kind of lucky that we're moving into it very quickly. So let's talk about the environmental considerations. So we first talked about a little bit of the market. So from a manufacturer point of view, the environmentals are extremely critical. When we make a product, we need to make sure it's going to survive in the environment it's put in. Oftentimes that means building from scratch, which we do for a specific marketplace. Well, Kima is a company that does testing. It's very, very famous worldwide for how they verify products are compliant with specific standards. In the power industry, Kima is kind of the #1 guys. What I'd like to impart upon you guys is to watch out for phrases like designed to meet 61850 or 61850 compliant or essentially compliant. A lot of these terms are marketing mumbo jumbo for, yeah, we'll probably work. But what you really want to make sure of is that the company has a third-party certification like a Kima certification that verifies, yes, indeed you are doing what you say you're going to do. Here's a certificate to prove it. We live in a day and age where a lot of people are taking liberties on spec sheets, so it's always good to double check. These certifications are very expensive, and it means that whoever has this, whoever the vendor you decided to go with, they've invested a lot of money and time to make sure the products are right. The certification is $100,000 per product, so it's pretty expensive, so you have to be pretty serious about doing it. Okay. I have a video here. I'm not sure it's going to show up well, but let's give it a shot. We'll go ahead and show you. This is a video of the actual 61850 switch being tested under 61850 circumstances. It's probably not coming out very well because it is a strobe light, and the strobe light can show you the bending of the chassis and the vibration that you're seeing with the device itself. And it's also showing twisting of the chassis itself and how it is surviving, operating while this test is going on. So chassis going up and down and twisting all at the same time. You can see the line and the gap in the modules and some of the pictures there that's showing how the chassis is twisting. So it doesn't look like it came out like a great video, but it's an example of how we do some real hardcore testing on these devices to make sure they pass. Now, something to consider or watch out for is that not everyone takes the actual construction as seriously as we do here, but it's always good to make sure the vendor is complying with what the actual certificate, the actual cert requires. It requires you to be compliant to 85C and down to -40C. So here's a picture of a product that does not comply with it because you can see the temperature range of the actual fiber transceiver, a very critical component in the communications, is not compliant with the standard. And so it's kind of strange how the product got to be certified, but it's always good to kind of check to see, was it built from the ground up? Were these nasty environments taken into consideration? If you look at the difference in our transceivers here, or a good transceiver I should say, you'll see that heat sinks are really required on anything fiber to make sure that they are transmitting and receiving in very hot temperatures and will be stable. So it's always good to look for those types of things within a product. Also, or additionally, you can see that you look at some of the embedded computers out there, they obviously produce a lot of heat because they have a main CPU or processor. So you need to get rid of that heat, and a lot of people will say, well, that's what a fan is for. But in this environment, fans are not a good idea because fans fail. And when fans fail, the devices stop working. So it's important to design a product from the ground up that will survive without any moving parts and that will be an efficient heat dissipation design. Not only with the heat sink and the way the heat pipe is attached to processors, but also in where all the other chips are placed on the board. You don't want to create a hot zone within the chassis. In this particular design, we're showing how a heat sink can be placed on the side of the unit so that heat will go up the side of the rack instead of stacking directly on top of another product. So if you had a heat sink in the middle of the product, say, it would just create a hot spot in the middle and then heat up the middle of the next device on top of it, causing an even hotter situation. So you really want to avoid that. This is a good example of how you can do that. There's a couple of vendors that currently participate in this way of dissipating heat. It's a great idea. So back to KEMA real quick. So not only does KEMA do environmentals, they also test the actual data communication. So they use goose messages is a very critical part of communication within a 61850 type of environment. Basically, it's a message that gives status to a safety relay and from the devices it's talking to, from the other IEDs. Well, this goose message, or general object oriented substation event message, has to be done without ever dropping a packet. It has to be guaranteed it's going to be delivered and has to take priority over all other communications. So KEMA does test for this, and when they did, it was, of course, it's very, very good to see a pass on that. There are some manufacturers that weren't very efficient at doing this, and that led them into some trouble. Okay. One of the reasons why other manufacturers may not have been as efficient with this is because there can be a limitation that most consumers or users are not aware of. And this is a thing called a full back or switch fabric or wire speed. They're all the same names for making sure that every single port on the communication device has the ability to transmit and receive at full bandwidth at the same time. And this particular product that we're showing here in the diagram, it uses two chips to support all the ports on the switch. And in between those two chips, there is a little, call it like a pipe between the two or a bridge, that is only 2 gigs big. So if the switch chip on the right is transmitting and receiving at 5.6 gigs, and the switch on the left is transmitting and receiving at 3.6, how can you expect all of that data to be able to go through that bridge in the middle that's only 2 gigs? You can't, and that causes delays. And the delay in a substation can be problematic because then you're starting to see, latency build up over time. The bigger the packet, the bigger the problem. So it is actually worthwhile making sure that whichever vendor you choose, whether it's a computer or a switch, you should make sure that it has full backplane, full bandwidth capability so that you don't see any delays in communication. Unfortunately, it's surprising to see that there were still some switches on the market available that have that backplane limitation. Okay, so we're still kind of in the physical / mechanical design and whatnot realm, and here you'll see that you need to be able to guarantee delivery under really bad environments where EMC is an issue, whether it's radiated RFI or if it's ESD, static, whatnot, or even some surges on the line. You'll see the big difference between a commercial switch, like what you'd buy a Cisco, an industrial switch, which is like your Moxa standard industrial switch, or there's some other names out there, and then you get all the way up to substations, even more robust than an industrial switch. So you really do have to build these things from the ground up with your environment in mind. Otherwise, it will not pass the stringent certifications. And the certs are there because it's critical architecture, critical infrastructure they're protecting. I mean, the communication now is part of that critical path to make sure your power stays on. So they have to be a little bit cautious, and that's why the specs are so high. So let's talk about the protocol. The protocol itself, for those of you who don't know what a protocol is, well, hey, I have a feeling most people know what that is on the line here, so we're going to talk about what is the protocol for 62850. Well, there's a lot of different protocols it uses or standards to follow, but really there's really just three that we'll talk about here in a moment. But before we go into the details of the protocol, I just want to show you why it's important to use a protocol that's the same. So let's just say that your substation, which is the blue box there, wants to know how much power is going to be needed at an electrical vehicle charging station, for instance. Maybe there's 10 cars in the vicinity that all plug in around the same time and demand lots of power. These cars, they have batteries that are 85 kilowatts power. I mean, that's a lot of power that you can put in. To put in perspective, that's almost a full week of a 4-bedroom house's power consumption. So, that's a lot of juice that these guys are requiring in about 4 hours. So your demand is going to go up from a substation perspective. But what if you had the capability of knowing, okay, hey, I just saw someone plugged into this charger. I know, likely, based on history, that for the next 4 hours that I'm going to need to put a little extra power to that portion of the grid because all these cars are plugged in from their daily commute to work. But what if, in the future, you decide to use this protocol and you could say, hey, car, I'm having some problem getting enough power. Do you mind letting me borrow some from your battery bank to supplement the power in the grid right now? So it's kind of like a demand generation. It's a demand generation event, and you can take power from them, maybe give them a credit, or provide a lower price for the energy they do use to charge a car. Those kinds of things. That same philosophy can apply to a lot of different scenarios, whether it's someone's solar system at their home, knowing that they do have solar, they are producing during a certain period of time during the day. You'll know when and where your extra power is coming from on the grid because everything's speaking the same language. Then you become more efficient. You'll see lots of different enterprise software into the mix, making everything much more efficient and much more redundant. Pretty cool. So let's check it out here. We have kind of like a visualized way of how this communication works in 62850. Now, it's not people talking to each other, it's devices, but in this scenario, we're just using this example. This guy here is saying, hey, I've got current, hey, I'm over current. So the merging unit says, I'm over current, there's a problem here, or maybe the frequency is off, whatever it is. And it reports that back to the protection relay. The protection relay says, oh, okay, I understand, that's a problem. We need to cut the power line now, cut that power output. So it talks to the ICU, any other IED that's able to do that. It says, okay, you better cut the line. And so they say, okay, I'll cut the line. And they send back to the protection relay, I cut it so that you know. And then protection relay says, okay, SCADA, I'll let you know that an alarm because I had to do these things. So now you're aware of what I did while you were sitting at your desk. So what does that translate to? Really, these are the protocols that are used within 61850. So your sample measure value is, or SMV, is what's happening between the merging unit and protection relay, and it's using that particular protocol to report back to the IED. And the same thing with Goose. The Goose messages are between a control unit or any other IED and the protection relay, just kind of letting them know what's been done, what event has occurred. And then of course everything that does happen and you want to represent on a SCADA somehow, that's done via MMS protocol, which is very similar to almost like an SNMP from the IT side of things, but MMS gives you the status of things going on in the substation. So what's really cool about that is it gives you a very simple way of looking at how these protocols are utilized and whatnot. We're not going to go much deeper than that about the protocols because it gets a little more complicated, but hopefully this is a good introduction. Maybe just a little bit deeper from a Goose message perspective, but not much. Basically, I just wanted to let you know that Goose messages, they're very common. They do need to have priority, but the way that they work is that they work via IGMP, which is a multicast message. So your IEDs will send a message via IGMP, and what the intelligent device in the middle will do, or the switch, will say, okay, I see this IGMP message. Has anyone subscribed to this message? And if they have, I'll send it to them. Without IGMP, what will happen is that an IED might send some information, and it'll have to be broadcast to everybody. The problem with that is that not everybody wants to hear it, and that becomes very inefficient bandwidth-wise on your network. So you really want to keep that bandwidth under control so that messages get through in a timely manner. And IGMP is a way to do that, and that's what Goose messages, that's how they're used today. So why do you want to spend money on IEC 62050 if you haven't already? We're still in the developmental phases of this and kind of getting our feet wet with 62050, but some of the biggest guys out there are doing it. Con Ed and SCE and Duke Energy are all looking at 62150 and have all tried out some of this in the field already. But there's lots of different reasons here. Obviously there's lower installation costs, modern networking technology, standardization, lots of different things. But really, I'm a bottom line kind of guy, and I think most people are too when it comes down to it. We're really looking at the increase in efficiency, the decrease in money spent on the generation of power. At 20% is a pretty big number, and that applies to a lot of different things. If you implement a full 61850 and everything is connected and you know what's going on, you can expect to decrease your need for power by 20% because you're able to do demand generation. You're able to shift power around to where it's needed, when it's needed, more appropriately. You can expect a 20% reduction at least in cabling. Now, that picture up on top there isn't a joke. It's actually a real substation that's utilizing lots of copper cabling for every single point it's measuring. If you start throwing that on an Ethernet network instead, you'll find that you need much fewer cables. It's much more efficient, much easier to troubleshoot, and much faster to install. And then, of course, 20% decrease in the monitoring, physical monitoring or manpower required to monitor these things because it's all automated with SCADA and whatnot more appropriately with better information. There's a lot more information, a lot more advantages too here. Obviously, demand pricing too is another concept where during specific points in time during the day, you can actually change the price of power, whether it's up or down. You can do that real time based on what you have to pay for power instead of having to try to average that. You have interoperability between brands and utilities more than you ever have before. It's still something we're all working on, but it is something that is, one of the tangible benefits of 61850. Demand response capability, you have more transparency for the customers or to the customers. They can actually see real time what's going on the network, how they can become more efficient, and when they know how they can become more efficient, or if they're being power hogs, they generally will reduce their consumption, thus making it easier to maintain your existing generation scheme. And a few other things there too, of course, like reliability is a very important point. Okay. So let's go into the mindset real quick here. It's complex. 61850 is a very big topic. Just this ABB manual alone, talking about 61850, it's over 230 pages. Just a manual for a specific product talking about 61850. You can imagine how much more complicated it gets. So the key is to try to make it simple as possible, but really there's thousands and thousands of pages. If you look at the IEC standards down here, there's lots of different aspects of 61850 you need to be familiar with. So my suggestion is, take it a step at a time, do the things you can now, build for the future. If you can't do it all at one time, it's okay. You can implement some of it. Maybe some of your hardware is ready to upgrade when possible, but when the time comes, at least you'll be ready and you'll have to reinvest in your new hardware. We talked about that convergence too, of course. That's the mindset is being able to converge everything into one single bus. So that's an important concept. So really, in the mindset, it's best to plan for the future. Implement some of 61850. Follow the rules when you're implementing, and don't forget about security. That is a very hot topic right now. Even if you don't have to comply with NERC-CIP, it's a good idea to maybe think about using those best practices. So with the new hardware out there, a lot of them they're compliant, but you have to actually use the appropriate settings. So pay attention to that. So our company, of course, we have a lot of successful substation deployments across all over the world, but there are many others that have deployed substation 61850 deployments. So we're just scratching the surface in the U.S., but I know it's going to be something that will increase in popularity as we go. The very basic mindset that you should take, it basically involves three things. It's this triangle of system stability. The first thing you should always consider is how do you minimize the error probability, or any probability of errors. You want to minimize that as much as possible before you implement new technology or while you're implementing new technology. But in reality, you're always going to have some errors, so how do you detect them faster? The faster you detect them, better you can have a response to, which is, of course, the last part, optimize your error repairability. When you're able to repair things very quickly, obviously that's better for your entire system. So it might seem obvious, but those are the three things that you need to do. So how do you take those three concepts and apply them to some of the technologies available today in networking and computing? Let's take a look. Here's a picture of an ideal substation automation system. So really it's a process level all the way up to station level. And nowadays, the Ethernet network switching and computing, they're all fast enough and are precise enough to actually work all the way down to the process level. So we're going to start to see more and more devices in that area and arena as we continue forward with 61850. But today, I think most people are using it at the bay level and station level, and you'll probably see some of the things here that you're familiar with and how you connect them. But let's look at how we can apply those three key concepts: minimizing errors, detecting them faster, and then repairing as fast as possible based on that. We have some interesting communication technology and computing technology that applies to each of these. Let me go over them here specifically. Here's one example of a GUI that can make life a lot easier. Not everyone here on the call is Cisco certified, so they may not understand how to set up some of those complicated devices out there in the field. Here's an example of a GUI or a setup wizard that's built into the devices that are sold of a switch. So in this example, you would click Quick Settings. You would put in the time. That's not overly complicated. You can usually figure that out pretty well. Default the time synchronization to a server that is available, like time.nist. Then you decide whether or not you're doing 61850. If you say yes, you enable that with a checkbox up there. And you click Next. According to the standard, you must use redundancy within 61850. So in this particular screen, you would choose a redundancy scheme. In this one, we've shown a turbo ring, which is a ring protocol that's very, very fast at recovering, down to about 12 milliseconds. Now you choose the ports that are using that redundancy, the primary port and the secondary port. Pretty simple. Here you fill out VLANs. Now VLANs are a way of optimizing traffic on your Ethernet switch by segregating them. So for instance, port 1 might not need to talk to port 4, so therefore it should never really receive any of that traffic. If you use a VLAN, you can segregate those connections and make it more efficient. This is a very easy way of implementing VLAN on this particular GUI screen here, but if you're not sure what it is, we highly recommend that you talk to someone that understands networking a little bit more that can help you through the VLAN aspect. This is the most complicated part of the setup. It's still easy if you know what it is, but if you don't, you'll have to ask someone to help you. And it is part of best practices for 61850. And then mirror ports. Mirror ports are a way of saying, okay, on ports 24, 25, and 26, I want all the data that goes in and out of those ports to be sent to port 23, because then I can use that for historian or data logging, a way to make sure I have all the data sent somewhere I can record it for analysis in case something goes wrong. That is also a requirement for 61850, but also best practices, of course. IP address. Set the IP address of the Ethernet device. Now, if you don't know what an IP address is, you would fall into that category of mentally unstable, what's a protocol type of answer, people. But really, obviously, you should all know what a IP address is. You put it in here, then you're at the summary stage. Okay, summary of what you just did, and then that's it. It's finish button here. Probably the hardest part of the whole deal is clicking the activate button, and you're done. Now, so the reason I point this out, I'll go back here. The reason I point this out is that not everyone is a network engineer. It's nice to have a GUI like this that walks you through step by step to make sure that your application, your specific substation application, is set up correctly. And the way the GUI is oriented is oriented towards a a 61850 implementation for best practices. So if you make it through this GUI, this wizard, you will have something that meets those standards, which is great. You know, we're hoping that we'll see some other vendors that come out with something as easy as this. Another aspect of minimizing those errors is the quality of service. QoS is a way of prioritizing packets so that one will have priority over another. In this particular case, you have to use this priority with goose messages, with SMV, and even MMS. It's required as part of the standard. We want to give it priority over other protocols. But if you do that, then things will go much faster, and it is required. So that's built in. We showed you the screen before about making sure you're able to dissipate heat. You're minimizing the probability of errors if you're using products that won't overheat. That won't start having errors on a processor because it's running too hot. When you're using 61850, you can also integrate the communication devices like switches and the computing devices like embedded computers that are designed for substation in with your SCADA system. What that means is that in your SCADA you can actually see a picture of the communication device or the computer and know that its status is good. We're showing green here. I know in most substations the green is considered bad, but red is actually good from a line diagram, but that's okay. You get the gist of it. Okay, another feature for detecting errors faster would be a fiber check mechanism. Most people don't realize that fiber transceivers can wear out over time. So when that happens, you need to know when they're about to go out. Now this over time, what I mean is something like 8 to 10 years. That's a long time. So, but the bottom line is I think that you guys will be using a lot of this communication gear for the next 10 to 20 years. So it's probably a good idea to know if things are starting to wear out, get a notification sent via that MMS protocol that goes back to your SCADA system and says, hey, by the way, guy, all your IDs are working okay. I just want to let you know your communication infrastructure is at risk right now. The transceiver is getting a little old and the power is going down. You might want to consider replacing it. So definitely you want to monitor your fiber connections. It's important to do that. Maybe not for the first year, but a few years after that you'll definitely want to be doing that. From a detecting errors faster perspective on a computer, you need to be able to have MMS and SNMP based diagnostics for the devices within the computer. So the CPU, temperature, the memory, the storage, all those things, if you can monitor them outside of the software running on the PC, that can give you an out-of-band advantage, meaning that if there's a problem with any of those devices, it will definitely notify you instead of being stuck in a software program that is currently crashed. So this is a really great aspect. You should look for that in and any computers you decide to use moving forward. Now, redundancy is optimizing error repairability, of course. If you have a problem on the network, you can recover. And as one way to do that is via RSTP. Many people use that as their redundancy scheme. Now, it's okay, it's just not very fast. There are other technologies out there like turbo chain, turbo ring, those types of things. Some of them interoperate with RSTP, like a turbo chain would do that with RSTP, and you can use them together. But if you're able to minimize that recovery time, that's better. It's right around 12 milliseconds right now to be able to do that with some of these technologies mentioned here. When you start using RSTP, that goes up considerably. You know, in this particular scenario, if it were done with all RSTP, you'd be looking at probably 100 to 200 millisecond recovery time at least. So there are advantages with going with proprietary technologies. Although I understand some people are afraid of using them, that's fine. There's plenty of other standard technologies that you can use. They just won't be quite as fast. And then lastly, we kind of come into this evolution of technology now in Substation, and it's this new technology called PRP-HSR. It's another way of minimizing errors and also repairing very quickly, because when using this technology, you're able to recover from a failure on the network in 0 milliseconds. So you go from 12 milliseconds to 0 because you are using parallel paths and parallel communication structures to get the data through. And it's pretty neat new technology. I won't go into a great amount of detail here because we just don't have time, but it's something you'll see kind of coming in the future. Optimizing error repairability, again, is another one is for the APIs that we provide with our computers. And if there's system garbage, it's slowing down. Maybe many of you probably experience this as your computer gets older, it gets slower. That could be due to a memory leak or a variety of different problems. You can, if you're utilizing a smart recovery mechanism, that you can actually clean out all of that garbage and get the system back running as fast as possible. Same thing if your system crashes altogether. You know, if you have some of these automatic recovery tools, it will recover your entire image and start back up automatically. And that's really important in a substation when it's critical to get these things back up and running. So hopefully you see these 3 points: minimizing error probability, detecting the errors faster, and optimizing those repairabilities. They can really apply to a lot of the devices in a substation. Check out this information and more about the things we mentioned. Of course, you can download this presentation, but also white papers are available on MOX's webpage. You just go to the webpage and type in white papers into the search, and you have a whole list to choose from. But there's also a whole section dedicated to Substation. So you might want to check that out as well for additional information. So in summary, Smart Grid is good. 61850 is good. You don't have to be 61850 to still utilize communication technology and be smarter. The smarter you are, the more communication you have, the more computing you're utilizing, the more efficient you can be. Make sure you pick a qualified vendor who can minimize those errors, detect those errors quickly, and repair them just as fast. Those are 3 key criteria you're always going to want to look for regardless of the technology you're implementing. It's always a good way to look at it. And with that, we'll conclude the presentation portion of the webinar, and would love to open it up to questions for all of you that are out there. Make sure you hit your question bar and get that information in, and we'll discuss for a few more minutes here.
Well, Jim, thank you very much for that presentation. I'll give you a couple seconds, I should say, to catch your breath before we go into questions. And we will go into your questions. I do have one here from Michael. Michael asks, have you seen a lot of PRP and HSR networks installed? And I know you briefly went over that slide, so maybe spend a few more minutes on, you know, PRP and HSR.
All right, well, thanks for that question, Mike. Yes, PRP and HSR is really new. In fact, it's so new that most vendors are still coming out with their technology today, including Moxa. And we do have some pieces of hardware available, of course, but many people aren't really sure how to do it yet because it is such a fresh technology. But it is a standard, and it is capable across vendor lines, which is nice. But really, to answer your question quickly, is that no, there really isn't anybody implementing it extensively yet. but I do expect that to happen here in the future. So it's something to keep your eye on.
Great, thanks so much for sharing that additional insight, Jim. This next question I have is from Anna, and her question is, have you tested virtual machine compatibility with Moxa computers? So maybe shed some insight there.
Yes, that's a pretty advanced topic because virtual machines are really an IT technology in the past, but what we're seeing now with the early adopters out there is that they're implementing virtual machines for their substation computers. That will help with efficiency too, because now you have one box that's running multiple machines, and each machine is dedicated to a specific task. So yes, actually, with Moxa's newest devices out there, we have seen virtual machines being placed on them and running in the field. Again, it's kind of a new concept to most people in substation because it's, it's not something that's been used before. But it has been proven, and we have some of the bigger guys like SCE checking into this technology and seeing if it's applicable to what they have to work with out there. The alternative is to use a bunch of servers. Now you can do that, but with the horsepower nowadays available with i7 processors, boy, you can really get a really nice computer with an i7 processor on there with no fans, industrial rated, substation rated, and go to town with virtual machines. And that is being certified right now with our company with VMware so that it will be 100% compatible, and that certification should be finished probably by the end of this year, beginning of next year. It takes a little time to finalize all the details, but it is compatible today. Yes.
Great, thank you very much, Jim. I'm going to give a few more seconds to allow for more questions from the audience to come in. But thank you, Jim, again for your insight on this presentation and the topic. It looks like we did have another question come in, another one from Michael, so I will take this. Will the implementation of PRP and HSR eliminate the need for any proprietary redundancy? So your thoughts.
That's another very insightful comment there, Mike. I appreciate it. Yes, actually, I believe in the future that will eliminate the need for proprietary redundancy. The interesting part is that I think a lot of people are still using this RSTP stuff for their redundancy, but the newest revisions of IEC 61850 says that at certain levels you must use a bumpless technology or a technology that is able to recover with no delay, because some of the requirements are that the communication needs to occur within 2 milliseconds. And if during that communication there happens to be a problem on the network and needs to have recovered in faster than 2 milliseconds, if this new standard for HSR and PRP is able to meet that or beat that 2 milliseconds, which it can, of course, because it's 0, it's going to be the standard moving forward. But again, I think most people are just doing what they can today because there's a very limited amount of PRP and HSR hardware. And eventually PRP HSR hardware will be integrated directly into the IEDs themselves, so that even some of the devices like switches and what we're calling red boxes will not need to be used. It'll be directly to the devices themselves. So keep an eye on that as vendors produce more and more latest generation technology.
Great, thanks again, Jim. So with that, we're going to go ahead and conclude the webinar. So again, I'd like to thank Jim for his insight and knowledge on this particular topic, and thank you to everyone for your interest and participation. Thanks again for tuning in, and have a great rest of the week. Bye now.